Good morning, everyone. Today, I'll be talking about MovieGen, which is a state of the art text to video generation system. So, let's start with a simple thought exercise. Imagine a fluffy koala bear surfing. Unless you've actually seen these talented type of animals surfing, this is not really a scene you must have encountered in real life. I'll also sprinkle in a little more detail. Let's think that the koala bear has a grey round nose and it's holding the yellow surfboard with its paws, and we have the sun backlighting it. Now, this is obviously a scene that we've not encountered in real life. But for humans, this is something that we have the power of imagining to a reasonably large amount of detail. We now have AI systems that can do the same. So, given this text prompt to a MovieGen model, we are able to generate a video that looks like this. We have the koala bear surfing, we have the waves splashing, you see the physics of the water, you see the physics of the lighting, and the fur and the light being reflected from the fur. We have these systems that generate these videos to a remarkable amount of detail. So, this is the problem of text to video generation. Where given a text prompt, we're asking a model to generate a video for us. And we have AI models that generate this high quality video now. So, what are the applications of these text to video generation models? Well, we can generate great videos at a low cost. And this means these models can serve as a great collaborative tool for social media content creators. In fact, these models are reaching to a quality point where they even serve as high quality collaborative tools for Hollywood creators, as we'll see in a bit. So let's look at an example video created by one of our content creators using a MovieGen model, and where now we have two meme legends who are going to battle it out in a boxing ring. And as you can imagine, getting these two to actually fight in a boxing ring is going to be really challenging. But with a few clicks and a few words, we can actually have a system that generates this high quality video for us. So, text to video generation is, of course, a very well studied problem. We've been studying this problem at least since 2017, where one of the first video generation systems was generating these digits that moved around. And increasing complexity of video generation models has sort of brought us to 2024. And with every generation of these video generation systems, we are generating videos that are more colorful, aesthetically pleasing, high resolution, longer in time, and so on. And in particular, I'd like to call out two systems that we worked on at Meta. Make a Video that we did in September 2022, which generates high quality, colorful videos, and Meta's Emu Video that we released in November 2023 that also generates high quality videos and powers one of our slash animate generations in Meta AI. So given these text to video systems, today I'm going to focus on these generations and really going to tell you what the challenges for these systems are, where we'll focus on the compute complexity, the modeling complexity of what this text to video task entails. And then tell you the key improvements that we did for MovieGen, where we scaled the compute, where we improved the training objective and the architecture, and we improved the data curation pipelines. I'll then compare our model and show some results by looking at our generations compared to those of existing state-of-the-art methods. And finally, I'll talk about scaling laws that show us that the future is really in scaling these models even more, and we can expect better video generations. So let's look at the key challenges for text-to-video generation models. The text-to-video generation problem is a very underspecified problem. We start with a few words as input given to a system, and then we're asking it to generate millions of pixels, adding lots of detail, imagining lots of detail to the scene. And so, given these half a dozen words or a few dozen words, we expect the system to think about how the scene will be set up, how the objects will interact, how they'll move, how the physics of the system will look like, how the lighting, how the geometry. And so the model really needs to perform a very ginormous task when it's going from a few input words to this high dimensional video output. When we're generating these videos, we also want the system to generate videos that are consistent and high quality. We don't want it, for example, to generate videos that are aesthetically pleasing, but where the object barely moves. We also don't want it to generate videos where the object moves and then is not visually consistent, so it disintegrates into nothingness. And finally, we also care about the visual appeal of the pixels. We don't want videos that are generated to have low pixel quality. And so, in general, tackling both visual consistency and quality is a pretty daunting task. And finally, the computational complexity of the text to video task is enormous. Given these few words of the text prompt as input, we have a model that takes teraflops worth of compute to generate each single video. And this is primarily because of the millions of pixels that we're generating. So for each video, the number of pixels scales with its spatial resolution and the temporal length. So the time, the height, and the width of the video. And just as a concrete data point, for a 10-second HD video, we're generating 500 million pixels. And so this model really needs to predict all of these 500 million pixels, predict this very high dimensional output, and then generate a video, which is a computationally intense task. So in general, most of the systems that have evolved for text to video have really tried to address these three primary challenges. And with each generation of text to video systems, we have these videos that have increasing resolution, increasing temporal length, and increasing visual consistency and quality. And in 2024, we released MovieGen, which is Meta's state-of-the-art text to video generation system. In primarily, this advances our text to video capabilities compared to competitors. We also introduced two additional capabilities called MovieGen Video Personalization and MovieGen Video Editing, which build on top of this video generation model. So let's take a look at what MovieGen is. MovieGen is a cast of media foundation models, where we start with a text-to-image system, which we train to generate images given a text prompt on billions of images. We take this system and further train it for the text-to-video generation task on hundreds of millions of videos, where now the model can take a text prompt as input and generate videos. We can then take this foundational text-to-video model and fine-tune it for different purposes. For example, we can fine-tune it for high-quality text-to-video generation, and this model is what we call the MovieGen video model. We can fine-tune it for personalization, which we call the MovieGen video personalized model, and we can fine-tune it for video editing, which we call the MovieGen video edit model. And let me show you a couple of examples of what these models can do. So the MovieGen video personalized model can take the input as a person's face and a text prompt. And so in this case, we have this person's face on the top right corner, and we ask the system to create a video for this particular person enjoying a drink in the desert. And what we find is that the generated video actually maintains the identity of the person and generates a very realistic looking video of this person, personalizing that video given that input face. For the MovieGen edit model, we can take an input video, here shown on the top left, and we can specify an edit in natural language, and we can ask the model to edit that video. For example, we can make the poodle wear a pink onesie, or we can change the color of the poodle, or we can change the background. And so this just allows us to specify these free-form edits, and now we actually get a video editing model, which is very fun to use. Now, the quality of these video generation systems has improved significantly. And in fact, for MovieGen, we found that a bunch of Hollywood creators find these tools to be very useful for collaboration. In this case, we collaborated with Anish from Blumhouse, who took a video that he shot when he was 10 years old. And now he's able to improve that video and enhance it using the MovieGen model, all at a low cost. So let's look at what Anish did.
This is a movie I made when I was 10. It's super cringe now, but I remember when I made it, I wanted it to be set in Manhattan. Okay, not quite Manhattan, but for 10-year-old me, dude, that's kind of incredible.
So now let's take a look at what the MovieGen cast of foundation models is and how do we train this. So like I said before, we start with the text-to-image system, which we train further for text-to-video, and then fine-tune it for video generation video personalization, or video editing. And in this talk, I'm really going to focus on the video generation aspect. We have released a tech report on Archive which contains all of these details. And so you can read this and actually find out more about the personalization or the editing model. And in fact, even a movie gen audio model that can generate audio given a particular video. Now let's focus on the key improvements for movie gen video. The first improvement that we focused for movie gen was to improve the model architecture and the training objective. And this enabled us to train the system at large scale in a stable manner. This next thing we focused on was scaling up the model parameters, the compute, and the training data. And finally, we improved the training data quality, which led to a significant improvement of the model's generations. So here's a system overview of MovieGen. We take an input video and we feed it to a TA encoder that converts it into a bunch of patches. These video patches are fed into a transformer. The transformer also takes in the second input, which is a text prompt. Now, to take the text prompt, we converted it into a bunch of text embeddings. And in this case, we use 3 different text encoders to do that. Each of these text encoders captures different types of semantic inputs and structural inputs about the text. And finally, by concatenating these 3 embeddings, we have a rich understanding of what the user wanted from this system. This text embedding is fed to the transformer using a cross-attention block that fuses this information with the video information and allows the transformer block to now create a video that depends on the text. Finally, after generating this video from the transformer, we feed it to a TAN decoder that converts it from the latent space to the pixel space. So why do we need this TAE encoder? Well, generating videos in raw pixel space is computationally really expensive. So in our case, we take a TAE encoder which takes these input frames which are in pixel space and converts them by compressing them into a latent representation. And we compress this video by a factor of 8 across the time, the height, and the width dimension. And now the transformer can operate on this compressed visual space rather than the raw pixel space, which makes it a lot more compute efficient. And in our case, given this 8 times compression across time, height, and width, this results in compute saving of more than 500 times. So this TAE is a very core component of enabling high resolution, high temporal length training. The second thing we focused on was improving the training objective. And in MovieGen, we use a training objective called flow matching. We take an original video and we interpolate it with Gaussian noise to create a noised video. Now, this noised video is fed to our model, which predicts the difference between the original video and the noised video. And essentially, it's predicting the direction in which the noised video needs to be changed in order to make it closer to an original video. With this very simple training objective, what we can do at inference is give this model a video that is basically pure noise and then ask it to iteratively denoise it in order to produce these high quality visual pixels. And flow matching, we found, was actually better than the objectives used in prior work, for example, diffusion. So here's a comparison between flow matching and diffusion in terms of video quality. And we find that flow matching generates videos that are much higher quality than the diffusion models. And we also found that flow matching actually converges faster, which saves us on training compute. And so we decided to use this training objective for MovieGen. The next thing we focused on was scaling up the model, the training compute, the training data, and the output. So let's look at each of these axes in detail. For the model parameters, we scaled the model parameters by a factor of 10 to a 30 billion parameter transformer model. And we intentionally based this on the Llama 3 architecture so that we can enjoy the benefits of scaling and training stability. In terms of training compute, we increased that by an order of magnitude, and we trained this model on 6,000 GPUs. And this required us to have innovations like multi-resolution training, which I'll cover next, and writing custom CUDA and GPU parallel implementations, which we've detailed in our tech report. In terms of training data, we also increased that by an order of magnitude, and we trained this model on hundreds of millions of videos and billions of images. And this required us to create a data pipeline that could curate high quality image and video by taking a large pool of uncurated videos. Finally, in terms of video output, our model generates 4 times longer videos and 8 times more pixels than emu video. And it can actually generate videos with multiple aspect ratios and a higher frame rate, which means that the videos actually look better and have smoother motion. Now, what is the big challenge for scaling up? The biggest challenge for scaling up is actually the sequence length that comes for videos. So given an input video, we can convert it into a bunch of patches as before, and we have, of course, the height, the width, and the time dimensions. These video patches scale quadratically in the resolution and linearly in the length. And so given a video of h times w times t, I'll basically have h times w times t number of patches, which is my sequence length. When I feed that sequence length into a transformer, the self-attention, which scales quadratically in the sequence length, will now have a compute complexity of h times w times t, the whole squared. Which means that this is going to be a lot of compute as I try to increase the resolution and the length at the same time. So in order to tackle this, we proposed multi-resolution training, which is a way of reducing the compute complexity and slowly increasing it stage-wise. And this enables us to have high-quality video generations without spending a lot of training compute. So let's look at this pipeline in detail. We start first with a text-to-image training only. So in this case, we do not have a temporal axis, and the model is just training on low resolution images. So we have 256 pixel images, which means that we have 256 tokens per image. Now we take this system and then we further train it for text to video. And in this case, we still maintain the low resolution. So we have 256 pixel images and videos. And now in this case, the sequence length has increased from 256 tokens to 7,000 tokens. But at the same time, we can train this system at a low compute cost. And finally, we increase the spatial resolution to 768 pixels. And in this case, we have a sequence length of about 73,000 tokens. And so by just progressively increasing it, we only are spending the most amount of compute in the last stage, which is training at the high resolution pixels. And to go from 768 pixels to HD quality, we have a super resolution model at the end. The last thing that we did for MovieGen was to improve the training data. So in this case, we start with a large pool of videos and we have a multi-stage data filtering pipeline that gives us our curated training set used in the final training. So let's look at this multi-stage pipeline. We first start with visual filtering. That's really going to keep videos that are highly appealing in terms of visual quality. So we'll filter out videos that are low resolution, that do not meet our aspect ratio standards, that basically don't contain a lot of text, or basically also are high aesthetics. The second stage is motion filtering, where we only want to keep videos that have high quality motion. So we'll filter out videos that have jittery motion, that have slow motion, or other types of weird motion. In the third stage, we want to ensure concept diversity and concept coverage. So we end up running a deduplication and a resampling pipeline that makes sure that our videos capture the global distribution of concepts in the world. And finally, we do captioning using a Llama 3 video recognition model that creates detailed captions for each of these videos. And so we get captions for all of our hundreds of millions of training videos, which describe what's happening in the video and serve as a powerful signal for training our model. We also run a camera motion classifier that ends up classifying the different types of camera motion present in the video. And this allows our model to understand what different types of camera motions are. And at test time, we can ask it to do various different things with the camera motion as well. Finally, we end up getting a curated set of clip prompt pairs, which are used for training. So in terms of getting these video generations, we also want to evaluate them on how they perform versus competitors. So we propose a benchmark in this paper called MovieGen Bench, which is evaluating two diverse aspects of video generation. The first is looking at the video quality. So we're going to give two videos to a human annotator and ask them which video looks better. And so this is really looking at the visual quality, the pixel quality, the visual consistency of that video. In the second case, we're going to pose a question, but in this also show the text prompt. And we're asking the question, which video matches the text better? So this is really looking at whether the generated video aligns with the text and whether it's actually faithful to the input text prompt specified by the user. So given these two metrics, we can evaluate different aspects of video generation. When applied to generations, we also want to make sure that these generations are actually covering different concepts in the world. And so for Movie Gen Bench, we have a prompt set which is 3 times larger than previous benchmarks. And it covers a variety of different concepts. We have humans, unusual activities, scene, physics, camera motion, animal, unusual subjects, like that koala bear surfing, so that we can basically test out different aspects of our models generation. We also have a variety of different nouns and verbs in our set so that we can test different weaknesses of our models. Now, when we use MovieGen Bench to compare to competitors' generations, we find that the win rate of our model, the percentage of times that our model's generations are preferred over a competitor's, are actually quite high. Looking at overall quality, we find that MovieGen's generations are preferred significantly over the competitors. And in particular, in terms of realness and aesthetics, where humans are preferring our generations because they're more real and they're aesthetically pleasing compared to competitors. So this shows that MovieGen is actually a state-of-the-art video generation system when evaluated across a variety of different concepts. Now, given the state of the art, have we really solved this problem of text to video? So in our work, we actually conducted a study of scaling laws. So we trained various different models of various different parameter sizes at various varying amounts of compute. And we found that actually scaling the model parameters and the training compute shows an improving trend, which means that as we continue scaling, these models should keep getting better and better. Now I'll leave you with a compilation video of different video clips produced by our MovieGen model showing you the higher quality. So thank you for watching, and I hope you're as excited about the future of video generation as we are.